In a previous example, we looked at that CNN poll and we said if they really wanted to lower their margin of error, to decrease the width of their confidence interval, what they would need to do is increase their sample size. So a better question would be, well, what exactly did they need as a sample size? If 888 people weren't enough, how many more should they get? Should they have gone with 1,000? Should they have gone with 2,000? Because there's a cost associated with every new person we sample, and we really need to take that into account. So it turns out, if we know exactly what we want our width of our confidence interval, or error, or margin of error to be, we can take our margin of error formula and we can say, okay, well, if that's a set quantity and we don't know what n is, we can basically solve this equation for n. We could divide out, we could divide out the z star, blah, blah, blah. There's a bunch of things that we can do to get there. And essentially, if we do all of those things mathematically, we'd end up getting this formula. So n is equal to our z star squared over our margin of error squared times our p hat and q hat. So there's our formula. This formula, just to point it out, is on your formula sheet. You can see here, if we're talking about proportions, you have the sample size formula right beside it on our formula sheet. So nothing to memorize, nothing to use for a note card. Basically, we just need to know, how do we use that? And then there's two more important pieces besides plugging into that formula, which will definitely be tested on the next exam. One of those things is, if p hat's unknown, what we want to do is use the most conservative number or value of 0.5. Now, why is this the most conservative number? Now, again, I'm going to get mathy for a second. I didn't make you watch me solve that for n, but I'm going to get mathy here. Let's say that we're dealing with a 95% confidence interval. So we have a z star of 1.96, not 69. Let's say we know we want our margin of error. We're talking about that CNN poll. If it had been like 2%, that would have been a lot better. So maybe we want this to be 2%. Oops, 0.02. But we don't, there's no way before you go out and take a sample to know what p hat's going to be. We can use estimates from prior samples, especially if we were the CNN poll. We could use the last p hat that we had as an estimate. But if we don't know that, what we're looking at is, well, p hat, and let's go ahead and rewrite q hat as 1 minus p hat. So if we do this, we're going to have some constant. I'm just going to ignore these for a second. And we're going to have a p hat minus a p hat squared, right? Because I'm going to distribute this p hat. And then there's obviously a constant on both of these based on our z star squared, our critical value, and our margin of error. But we can ignore that for now, because I'm mostly interested in saying, well, what the heck is the shape of this? If we have some random coefficient on each of these, which is positive, well, if we're talking about graphing this, we have a p hat squared. So this is a quadratic, right? It's going to be a parabola. So this parabola we actually know a little bit more about, in fact, because if we go back to the factored form of this form, we know some stuff. We know if p hat is 0, well then our n is 0. Doesn't make sense. If p hat is 1, 100% of people or something, it's also 0. And that means our vertex of this parabola is at 0.5. And again, it's a downward facing parabola because we have a negative coefficient on the squared term. So we don't necessarily need to get too crazy into this, but I wanted to make sure that we understood the reason why, if we're plotting on this is our n versus our p hat, that the reason we use this 0.5 as our value is because it is the largest possible value of n that we can get out, based on the fact that this particular formula is a quadratic formula, and that's where the vertex of our parabola is. So this, insanely important. Make sure you realize that if I don't have it, I can use 0.5. In fact, so important, I'm going to pull up my formula sheet right now and put that in there as a note. If p hat unknown, use p hat equal to 0.5. So not 5%, which we end up getting kind of confused when we get to hypothesis testing, because if we don't have an alpha or significance level, we'll sometimes use the most common of 0.05, but 50%, the halfway, right? That's the worst case scenario. So this should be written on everyone's formula sheet. So now that we have that in, the second bullet point here, also important, our sample size is a number of people. So you have to make sure that you round this in a way that makes sense. You can't tell me that I need to go out and sample 935.2 people. You need to tell me a whole number of people. And if you round down, I might not get the margin of error out that I wanted. So you should always round up and be conservative. So this is another very important point to keep in mind for the exam. So let's see all of this in action in our example. So here we see a sociologist who wants to conduct a poll to estimate the percentage. So we're trying to estimate a proportion of the same thing, of Americans who judge that affirmative action programs for minorities and women should be continued at some level. What sample size, okay, so we know what we're looking for, what sample size should be obtained if she wishes the estimate to be within 3 percentage points with 95% confidence. So let's go ahead and first thing, since we know we're dealing with a sample size, we're going to go ahead and write down that formula for ourselves. In fact, it says here if she uses an estimate, blah, 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 but let's just write down the formula. So again, I'd go to my formula sheet, I'd grab it, n is equal to z star squared times p hat q hat divided by my margin of error squared. So z star, our critical value, squared times p hat times q hat all over my margin of error squared. This at least gives me the framework for figuring out what exactly has been given to me in the questions done. I have two ways to handle this. I could try to translate everything at the beginning, or I can use my formula to say, okay, what in the heck is supposed to be here, and then go look for it. So I'm going to try that other way to do this time. So first thing goes, all right, I need a z star. I know z star is something I can get from that t table as long as I have a confidence level, and we were given that. So we have a 95% is our confidence level, which I'm just going to denote CL. And we can use this to find a Z star from our table. 95% gives me a Z star of 1.96. So my Z star is 1.96. Don't forget the squares. That's a very common mistake. Those pieces that are squared, forgetting them. All right, so then we continue on. Next thing I need is a p hat. A p hat will be a sample proportion, right? So here we have that she used a 1999, very outdated, estimate of 85%. So that 85% is an estimate from a poll. So that is our sample proportion. So that's what we're going to use as our p hat. Right? This is a estimate, which means it's not the real thing. It's from a poll, telling us even more that it's a sample, and it is a percentage, which is another way to say proportion. And if our p hat is 0.85, that means my q hat is 1 minus that, it's 0.15. The last piece we need is our acceptable margin of error. Now, at no point do we call out the margin of error explicitly, but we do say that she wishes the estimate to be within 3 percentage points. Within is your keyword to let you know that we're dealing with a margin of error. Now, it is a percent. That's its units, right? We want to say 8.85 plus or minus 0.03. So you need to enter this as a decimal and also make sure you don't forget to square it. So that's our formula for finding our sample size. All right, so I'm going to just do all of this at once. There's no reason to do this in steps since it's all multiplication. No issues needing parentheses or any of that jazz. It's only really necessary when we have addition or subtraction that we're worried about. So all that together looks like we get 544.2. And that's when we remember the second bullet point. It has to be a whole number. We need to round this up. So she needs to sample 554 people. Did I say 554? I did. 545 people. All right, so the next question says, what about if she didn't use any prior estimates? So what are they telling us to get rid of now? They're saying, let's get rid of p hat. It's unknown. So I want you guys take a second, pause the video, do this calculation on your own, and then come back and check if you did it correctly. So we're using the exact same formula. We're still doing a 95% confidence interval, so there's no reason to change my z. We still want to be within 3 percentage points. My margin of error hasn't changed. The only thing that's changed is we're not going to use that incredibly, horribly outdated 1999 estimate. We're going to go ahead and say, oh, well, if I don't know what it is, and I don't believe this is at all accurate because it's so outdated, I should use 0.5 and 0.5 because we don't know our p hat. We want to go to that top of the vertex of our parabola. So if you plug all that in, what do we end up with? I should have just edited the last one. It's too late now, too far in. We get 1067.1. And then remember, we need to round up. And this is going to be 1068 people. Now our last piece here says, let's go ahead and compare those results. Basically, they want us to realize without a prior estimate for b hat, we needed almost twice as many people. So having a prior estimate is very useful. Doing some sort of small pilot, something that could be very useful. This is obviously a very extreme case. If you think about my parabola, since our actual original 0.85 is so close to the extremes of this parabola, right? Oops, over here. That's why we're seeing such a big difference between 0.85 and 0.5. If our p hat had been something closer to 50%, it wouldn't have been as extreme a difference. But in that case, it may make sense to just be conservative and use the 0.5 just in case your sample doesn't come up with exactly the same p hat as what you expected or something a little closer to 0.5. All right, I don't know what's next, so I'm going to look forward. Okay, cool. We have a really good example. I'm going to go ahead and do that one in a separate video because it is kind of long and it's really important.